Welcome Mechanics of Materials students. In this quick demo problem we're going to demonstrate application of shear strain, and by shear strain we are referencing engineering strain, usually going by the Greek letter gamma, which gives us a measure of the change in angle of based on two orthogonal reference directions that were originally orthogonal at pi over 2 or 90 degrees apart. And as the result of either changes in the x direction of the y face or in the y direction of something on the x face, we end up getting a change from that 2 pi down to something less than 2 pi. So shear strain is always defined as positive if we're going to a smaller angle. If something was originally a right angle and we get something less than 90 degrees, we have positive shear strain. So it is an angular measurement. So it, in this case, is defined as pi over 2 minus beta. And I guess we can basically show these other two angles. So we could say that would be equal to, in this case, the angles, let's get another angle, call it phi. So it would be, in this case, alpha plus phi. So it's the change from an originally perpendicular configuration to something less or something more. And as was the case for normal strain, we are defining strain as the difference. So if we look over here, we're going to look at a couple of points. So we're going to start off with point A, and we're asked what is the average shear strain at point A, and that's an average because we could have had maybe a different shear strain as we go from A to some point over here. We're assuming this whole body basically deforms uniformly, so we have the same shear strain all the way across. So we're told that a point that was originally here moves down here by 0.0051 inches. So we can look at our original angles of maybe A, B, and we'll call it C over here, was 90 degrees. And because of C's displacement, we've introduced this angle, we'll call it theta. And we can determine theta as a tan of 0.0051 inches. That's our opposite divided by the adjacent, 1.7 inches. And so that equals theta. So theta ends up being, grab our calculator here and calculate theta, 0.0051, enter, 1.7 divide, so that's the argument of the arctangent is 0.003 atan, so that gives me 172 degrees, but I need this in radians to define strain. So 180 divide 3.14159 times, and I get about 3 times 10 to the minus 3. Okay, now that's just angle theta. So we're looking at this angle. Now we go back to our definition of engineering shear strain and say, okay, how does theta kind of tally up with the angles here? Well, we could look and say, you know, theta in this case would be the equivalent of alpha or phi. So it is the difference. It isn't the new angle beta. But notice that a positive engineering shear strain is defined by an angle that reduces what was originally perpendicular. In this case, our angle theta is resulting in something going from 90 degrees to something going to more than 90 degrees. So BA, we'll call it C prime, is more than 90 degrees. So in actuality, the gamma at point A, the engineering shear strain at point A, is going to be negative because it's resulting in an increase of the angle in that corner from 90 degrees to something more. And we're going to define that in radians, and we're going to actually define it in terms of microstrain because it's a little bit easier. So this would end up being negative 3,000 microstrain units. Microstrain. So that was pretty simple. So basically, with shear strain, we're looking for angles. How did the angle at any point of two orthogonal directions change? Did it get bigger? Did it get smaller? By how much? So, and it can be due, in this case, that angular change was due to a displacement in, if we defined x and y this way, we're looking at something on the x face of the body displacing in the y direction. So we're looking at this kind of displacement. We could have achieved the same thing by having something on the y face displacing in the x direction. So we could achieve it going like that as well. But that's not what we had. So the $6,400 question, which probably isn't worth as much as it used to be, is what's the engineering shear strain at B? And without going through any math at all, we know that we're going to have the same angle theta up here because we have the same opposite over adjacent. We have the same right triangle basically. But in this case, we did actually define a smaller angle. Rather than being 90 degrees, AB, we'll call it D, was 90 degrees. Going from an angle that is defined as AB, call it D prime, is less than 90 degrees. So we have positive engineering shear strain at point B. It's the same magnitude that we had at point A, but it's going to be the opposite sign. So we have 3,000 microstrain engineering shear strain at point B.